simple way to solve the all-pair shorted path is by running a single source shorted path algorithm v times, once for each vertex as the source. Then, if the edges are no-negative, we can run the Dijkstra's algorithm. If we use the linear array implementation, the running time is big O of v cubed. Otherwise, if we implement using the binary min heap, the running time will be VE log V, because this is bigger than this. If it has some negative weight edges, we have to use the Bellman-Ford algorithm. And its running time is big O of V squared E. And on a dense graph, E is big O of V squared, so it is big O of V to the fourth. So we need a fasting algorithm. It is Floyd-Warshall algorithm, and its running time is theta of V cubed. First, I'll remind you of this adjacency matrix. What is this? Park Jong-hun. What is the adjacency matrix? Wij. Okay. Wij. What is the meaning of this? Which weight? Yeah, the weight of the edge from I to j. Yes, so look at this. The entry W12 is 3 because the weight of this edge from 1 to 2 is 3. So all the other entries are calculated in this way. And look at this. It means the edge weight from vertex 2 and vertex 2, vertex 1. There is no edge, so the weight is infinity. Okay, so this is the input of the Floyd-Warshall algorithm. And then the output is this, shortest distance matrix. So each entry D sub ij is delta of ij. It is the shortest path distance from I to j. Okay, then let's see. This is entry 2, 3. It's minus 4. What does it mean? 박근배. Okay, what is the meaning of this? Which path? Longest? Shortest path, yes. The shortest path weight from vertex 2 to vertex 3 is minus 4. So we are going to calculate this. This is the result. So we calculate this for every vertex pair. And look at this. They are zeros on the main diagonal because the path from I to I is 0. And the path weight is 0. Unless there is a negative wave cycle. If there is a negative wave cycle, these values can be negative. So we can detect whether negative wave cycles are. And there is another output. It is the predecessor matrix, pi. So, look at this. It is entry pi 1, 2. It means its value is 3. The meaning is there is a path from, shorted path from vertex 1 to vertex 2. Okay? The shortest path distance is stored in the D matrix. In the pi matrix, 3 is stored. It means the predecessor of vertex 2 is 3 in the shortest path. And then we can construct the whole shortest path by consulting this matrix several times. Then which entry should we consult to find the predecessor of 3? 김범진. 장영민. Which entry should we consult to find the predecessor of 3 in this case? 배민희. 신지수. 박준규. 최소리.
아까 shortest distance 매트릭스 한 거에서 거기서 구한 길에서 도착 지점에 조상 찾으면 되는 거예요.
So it is stored here. It is stored in this matrix. Which entry should we consult? 김종빈. Yes. 1, 3. In the entry pi 1, 3, the predecessor of 3 in the shortest path from 1 to 3 is stored. Okay? Then the predecessor of 3 is 4. And next, 신경식. Okay, what's next? The predecessor of 4 in this shortest path. 어미송. Yes, we have to check out the entry 1, 4. So it's 5. And next, 손광훈. What's the predecessor of 5? Yes, we have to check out the entry 1, 5. 1, 5, it's 1. So this is the shortest path from 1 to 2. So if this predecessor matrix is given, we can construct the shortest path between 2 vertices in this way. And look at this. In this case, they are not defined initially, and if there is no negative wave cycle, all the values will be nil at the end. Okay, this pseudocode is what I did now. Okay, now I'll explain the Floyd-Warshall algorithm to calculate these two matrices D and pi from W. First, I will define intermediate vertices. An intermediate vertex of a simple path from V1 to VL is any vertex in this path except V1 and VL. All the other vertices are intermediate vertices. And Floyd-Warshall algorithm is based on the observation of the intermediate vertices, which cost theta of V cubed time. Let the set of vertex is numbers. Vertex 1, vertex 2, vertex 3. So these are vertex names. And then, for any pair of vertices, ij, consider all paths from I to j whose intermediate vertices are all drawn from 1 to k. And let P be the minimum weight path from among them. Then the path can be calculated into two categories, divided into two categories. If K is not an intermediate vertex, then all intermediate vertices is from 1 to k minus 1. If K is an intermediate vertex, then we can break the path into two parts, from I to k and k to j, and these two subpaths don't include k. Why? Because there is no negative wave cycles. If k is in, there is an optimal shortest path without k. Okay, I'll explain using this example first. Initially, we initialize D0 and pi 0. And then we calculate D1 and pi 1 from the previous matrices. And then D2, pi 2, D3, pi 3 in this way. So first I will explain the D matrix only, the shortest path distance matrix. The D0 is the weight, the adjacency matrix. D0 means there is zero intermediate vertex, no intermediate vertex. It means only shortest paths have only one edge at most. So it is the same as the adjacency matrix. Okay? And then D1 is, it may have an intermediate vertex, and the vertex name is 1. So you can go from vertex I to vertex j through vertex 1. So one possibility is added. And D2 is you can add vertex 2. So you may use vertex 1 and vertex 2 or any subset of them. Okay, let me show you how to calculate between the D matrices. So this is the 3 matrix. It means, look at this. The entry 1, 2 is 8. It means the shortest path distance from 1 to 3 is 8. And the intermediate vertices can be vertex 1, vertex 2, or vertex 3. You can use all of them or none of them or any subset of them. In all combinations, this is the shortest path. And now we are going to add vertex 4. Then one possibility is added. In this matrix, all possibilities without using vertex 4 is reflected. All possibilities, the minimum value of all the possibilities without vertex 4 is calculated here. So we only consider the possibility that vertex 4 is used. Then it is this. Okay. What is the meaning of this row? Kwon-daun. What is the meaning of this row? Yes, all shortest path from vertex 4. All shortest path distance from vertex 4. Kim Hyun-jun, what is the meaning of this column? Yes, all shortest path to vertex 4. Then we are going to calculate this for every vertex pair ij. From I to 4 and 4 to j. Okay? Then we take the minimum between these two values. In this case, vertex 4 isn't used. And then let's try the first row. The first row is calculated by adding 4 to these values. 4 plus 2 is 6. 4 minus 1 is 3. Minus 1, 4, 2. So we calculated this for all the values in the first row. In the first row, I is 1. So the path distance is 4. And then j is from 1 to 5. So these values, 4 to 1, 4 to 2, 4 to 3, 4 to 4, 4 to 5. And then we compare these values and take the minimum. We know that 0 is smaller than 6, so it's 0. And how about the others? This one. This one should be minus 4, negative 4. Okay? And then the next row. 문경식. Okay, what's the values in this row? 박영호, 이동우, 이정우. Okay, we add 1. In this case, I is changed to 2. Okay? So the value from 2 to 4 is 1. So we add 1 to all these values. And then what are they? 3, 0, negative 4, 1, negative 1. Then compare these values to previous values. And in this case, they are all smaller than previous values. So we use these values. And then the next row, when I is 3. 이종하, 7, 4, 0, 0, 3. And after the comparison, we reuse these values. 경명수. How about this? The same, because it is 0. Finally, in this case, it's 6. So they are 6. Sorry. 8, 5, 1, 6, 4. Then this is bigger than its previous value, so we reuse 0 in the table. So let's compare these with this. Are they the same? Yes, they are the same. So this is one iteration of the Floyd-Warshall algorithm. In the next round, we use vertex 4. In that case, we use this column and this row. Here. This column and this row. And then what is the time complexity used in an iteration? 최용준. 한상현. 강인구. N squared. Yes, we calculated all N squared entries, but it takes just constant time to calculate only one entry. So the running time is N squared. And how many tables do we calculate? We calculate from D0 to n. So we calculate n tables. So the running time is n cubed, simply. Okay? And another. What is the space consumption of this algorithm? Park Sung-hyun, what is the space consumption of this algorithm? N cubed, right. All the space required to store all the tables takes n cubed space. But can you reduce the space? More exactly, when we calculate D3, we only need D2. So first we have D0 and D1. And then after D1 is calculated, we use this space for D2. And then we use this space for D3. So that's a simple space reduction. So we need only 2 n squared matrices. Okay? It's the same as we learned in assembly line scheduling. But we can do better. We need only 1 matrix. We don't have to maintain 2 matrices. We use only this. Why? We just write it in the original matrix. By comparing the new value with the old value, we store the minimum. Then there is some possibility that old values being used change it during this process. But we only read these values, right? In the previous table. Then let's compare those values in the new table. They are the same. So we don't have to worry about the possible changes of the old values. Why don't they change? The values in the diagonal are zeros. So when you calculate this, it's always 0, so it doesn't change. Or we add this, it doesn't change. Okay, it's a good observation. Then why the values on the main diagonal is always 0 during the whole process? Yes? And one thing is because there is no negative wave cycle in the graph. If there is one, these values can be negative. Okay, so we use only 1 table. And then the last one, the table pi. Let's look at the changes in this table. Which values are changing? This, and this. Okay, there are changes. So look at this. Its value is change it from 8 to -1. And let's look at the table pi. 4. And then it's entry 1, 3. And look at this. It's entry 1, 3. It was 1 in the table pi 3. And it is changed to 4 in this table. So why is it 4 in this table? Can you explain the reason? We can explain the reason why this value is changed to 4. How about this? Okay, it's still 4, right? Your hypothesis is right still now. How about this? It's 4. Now how about this? It's 1. There is a typo, right? Typo. Let's count how many typos are there. Then how about this? It's 4 and still 1. And 4, 3, 4. It's 3. So now we have to conclude. Are they typos, or is there any reason they are not 4? Okay, there is a reason. For the other cases, what is the definition of this? I will draw. Okay, I will use this. In this case, we use from 2 to 5, right? The shortest path from 2 to 4 and 4 to 5. In this case, fortunately, this was a direct edge. So 4 is the predecessor of 5. So 4 is stored. But in this case, the predecessor of 5 is 1. That's why we store 1 in this case. Then, okay, now you can understand. Then the question is, where is it stored? Where is the value 1 is stored? Value 1 stored? Look at this. It's from pi 3, 4, 5. Look at this. Pi 3, 4, 5. It's 1. Okay, I found it. Because it is 1, we write 1 here in the pi table. Understand? So this problem frequently appears in the final exam. So it depends on your decision. You can learn this perfectly and get the full score of this problem, or you already had a lot of score in the midterm, so you don't have to study this. Okay, it is very tricky. So that's why. So the formal description is the description of the D table is given here, and the formal description of the pi table is given here. So if the value doesn't change, we use the old value in the pi table. But if it changes, we take pi kj instead of pi ij in the previous table. That's this. Okay, I won't teach the transitive closure. This is the end of this class. So we have 30 minutes. So during that time, I'll get some personal one-to-one questions from you. Then you can ask me in Korean. And I have an announcement. And usually, the algorithm class has 3 exams: quiz 1, quiz 2, and final. Usually 40%, and 30%. But this time, the final exam includes the last 2 exams. So the percentage is 60%. So are you happy? But it's too early, I think. So you have to study more because the percentage is higher. And if you have any questions, come to me and ask me after this class. Okay, let's wrap up this class now, and good luck in the final exam.